We are going to look at resonance structures. Here you have phenol. The resonance starts with the lone pairs on the oxygen, curly arrow to move the pair of electrons, and then the pi bond opens up to the ortho position. And this double-headed arrow below to show the next resonance structure. The other structure I'm drawing here in green is the nitrobenzene. Here the oxygen has a negative charge and the benzene ring, and then the oxygen has a negative charge and the nitrogen has a positive and 4 bonds on it, nitrogen. So now this one, we can also move the pi bond towards the positive nitrogen to make a new pi bond, and then the negative oxygen can come back with the curly arrow. Then again the double-headed arrow to show the next resonance structure. So this is important to learn one benzene activating, which is ortho-para directives like the phenol, and the other one is nitrobenzene, is a benzene ring deactivating agent. So in the activating one, the ortho 2 positions and the 1 para position would be negatively charged at some point. So that's the importance of that one. Now when you look at the nitrobenzene, you only going to be getting a negative charge possible on the meta 2 positions. So that's the key, and it's better to learn them side by side. So the meta directive or the benzene deactivator, nitrobenzene, and the ortho para directive, the benzene activator, the phenol group or the OH, single bond OH, right? So that's the thing to compare side by side, 1 and 2. So, but I'm going to be showing the resonance structures separately. So let's start with phenol. So the phenol, the lone pair on the oxygen can move and pi bond opens up to the ortho position, right? And then the next structure with the double-headed arrow, and you have a double bond oxygen now, and the hydrogen stay the same, and then there's a positive charge created on the oxygen. It's actually positive. Now the 2 of the pi bond untouched, and this pi bond open to the ortho position, so it's a negative. Now that negative moves in to the neighboring pi bond, and the next resonance structure with the double-headed arrow, and this is a new pi bond, old pi bond, and the double bond O and the positive on the oxygen, right? So now we have a negative in the para position. We created that. Now that one moves to the right and the pi bond opens up, so we will create the new ortho negative position. So double bond OH and positive on the oxygen, and this bond is untouched. This is a new pi bond pre-created, and this is the negative new ortho position, right? So now this one can move to the open the pi bond and neutralize the positive on the oxygen. Now it's almost same as this, the beginning resonance structure. So it's actually, there's 1, 2, 3, 4, 5 structures total, because there's 2 different benzenes, right, by rotating the pi bonds. So that's how you get all of them. Now practice that. So the blue one, just to show you, the phenol is a weak acid and it can actually make the phenate ion and release the proton. So that's another trick you can see in some problems, right? So the phenate ion's stability can be explained using resonance structures. Now if we leave behind the proton, let's say it is there in the solution, so how do you do? Actually you can just cancel this proton and the positive charge on each of the drawings. So that's how basically the shortcut, if you think, to make the phenate ion resonance structures. So draw them and see whether it creates or satisfies, and that's the goal. Now also remember, like I mentioned, the ortho-para directive of the single bond oxygen, and also this is an equilibrium. Weak acid, its conjugate base, and the proton, it's an equilibrium, and you can explain the conjugate base stability using the resonance structures. So that's what we supposed to do, right? So okay, practice that, and the next one is nitrobenzene.